Hey, we're back. This is part two of heat of formation. We're actually going to go work through a worksheet and see if we can answer some of these questions. First one, state what the degree symbol means. The degree symbol in any kind of thermodynamics, delta HF, we have other things like delta S, delta G. If it's got a degree symbol, it means standard reaction conditions. That means 25 degrees Celsius or 273 Kelvin and 100 kPa pressure. If we get to electrochemistry, it also means 1 molar. Like if a solution is made, it has to be a standard 1 molar. These are standard conditions. If they were under different conditions, the delta H would be a different value. This is why it's important. So degree symbol, 25 degrees Celsius, 100 kPa. Define heat of formation. This is the energy change or enthalpy change when 1 mole of a compound is formed from elemental forms uh, under standard reaction conditions. Now, multiple choice, only one correct answer. Which species has 0 for its heat of formation? Things that have 0 for heat of formation are things in their elemental form. So if it was an elemental form, one, that's ozone. Can't be the third one because that's a liquid. And it can't be the fourth one because that is an ion. So it would have to be B. Oops, cross it out. There, so much for this. Let's try this differently. So B is the correct answer. So phases have to be important. As you know, there's an energy change with the phase change. So you have to have the correct phase. All right, B, which one has 0 heat of formation? Well, that would be elemental bromine. By the way, elemental bromine is a liquid at room temperature. It's not a gas, it's not an ion, and it's not monoatomic. So it has to be C. For iron, we're looking at solid iron because iron is not a liquid at 25 degrees and ions are not elemental forms. So there you go. We are going to write an equation for the heats of formation. That means we will have it yield 1 mole of the compound elemental form, under standard conditions, so that's going to be a liquid from elemental form. So hydrogen comes as a gas and diatomic. So does oxygen. It comes as a gas and diatomic, except we just need one of them, and therefore we need to have half of a mole of O2, because half of 2 is 1. So the delta H for this would be the heat of formation of water. The next one, KClO3, that's an L, not an I. So we're going to form 1 mole of potassium chlorate. It's an ionic compound, and therefore it's a solid at room temperature. Potassium is a metal, and therefore it's a solid. Chlorine is a diatomic thing. It's a gas, and we need one of them. It comes in pairs, so we have 1/2. And then we're going to need oxygen. It is diatomic and a gas. How do you get 3 out of 2? You're going to multiply this by 3/2 or 1.5, and you get a balanced equation. All right, rubbing alcohol. We're going to have C3H7OH. Now look, H7 and OH is be 8 hydrogens. So carbons are going to be a solid at room temperature. We need 3 of them. Hydrogen is diatomic and a gas at room temperature. We need 8 all day, so 4 times 2. And we need 1 oxygen, so we're going to need 1/2 of a mole of O2 gas. These would all be heats of formation reactions. The delta H for these equations would equal to heat of formation. That's what it is, but that's not how we're going to use it. How we're going to use it is this equation right here. So sigma P minus sigma R equals the delta H. Sounds all fancy because of all the Greek symbols. Delta H is the heat of the enthalpy change, and reaction just means any old chemical reaction. Sigma P would mean add up all the products, means add up all the products using the heats of formation. And then sigma R is add up all the reactants using heats of formation. And when you do this and subtract it, you end up with delta H for this equation. So this one, right off the bat, is tricky because we're looking for the heat of formation for propanol. I think I want to come back to that one. I think I want to do number 6 first. In this case, we want to solve for delta H. And we're going to be given heats of formation. So we're going to solve for this, and all these need to be given to us. So let's do that. Let's come up with a sigma P and sigma R, and it's going to equal to delta H. Now, we need a balanced equation first. So if you balance this, you're going to have 2 carbons. So we need 2 carbons. We're going to need 6 hydrogens all day, so that's going to be 3. We got 4 oxygens here and 3 here. That's going to be 7 all day over here. Here's 1, which means I need 6, so 3 of these guys. So that should be a balanced equation right there. It's important to have a balanced equation because every time you have a delta H given, it's per 1 mole. Well, we're going to add up the products, right? This will be sigma P. And how many moles of carbon dioxide do we have? We have 2 moles of carbon dioxide. So I'm going to put down these big square brackets. I'm going to put a 2 down here, parentheses, and minus 393.5. That is 2 moles of carbon dioxide. And sum of, add them up. I need 3 moles of water. So I'm going to have 3 times negative 282.8. Now these are kilojoules per mole. The coefficients are the moles, and therefore these are kilojoules. So now, this big brackety thing here is going to be sigma P. Now we got to subtract out sigma R. So minus, big square bracket, 1 of these. So that's going to be technically 1 times negative 277.6 plus 3 of these. I don't see it over here. 3 of these means 3 times 0 because oxygen is an elemental form and therefore has a 0 heat of formation. Now these right here is sigma P minus sigma R, so they're going to equal to the delta H for the balanced equation. It will equal to this once I add this up. All right, so now I added them up slowly, and for the sigma P, I got negative 1635.4. For the sigma R, I got a negative 277. And for total, I end up with 1357.8. And technically, I guess it should be 57.8, not 58, because even though this would end up being just 787, it is good to the 10th. Everything's good to the 10th, so it should be good to the 10th. So let me fix that. I got a big old fat marker here. So we negative 1357.8 kilojoules. That is delta H for this balanced equation. That is that number right there. Now let's go back to the previous one. The previous one, we just have our X in a different spot. So before, we were solving for delta H, and we were given everything else. In this case, we're going to be given delta H and all but 1. So X will be in here somewhere, and we need to solve for X. So you just set the problem up and then solve for X. So let's do that. Let's do sigma P minus sigma R. Sigma P we're going to need, and this is going to be a lot of numbers, big square brackets. We're going to need 8 times the negative 282.8 plus we're going to have 6 times negative 393.5. That is sigma P minus sigma R, and it's going to be 2 times X, because I don't know what that is. Technically, plus 9 times 0, and 9 times 0 is 0, and 2x plus 0 is 2x. So now this will equal to delta H. And in this case, we're given delta H for this balanced equation. This is the balanced equation, this is the balanced equation, so the delta H is for the balanced equation. Negative 4,018 kilojoules. So we can solve for this. This will be in kilojoules per mole, just like all the other delta H's are. And you stick a calculator to it. So I went through this math slowly and surely, and Don't call me Shirley. People often will set the problem up correctly, showing me they know how to do the thermodynamics, but then messed up the algebra. So first of all, you need to add these up. These are a negative plus a negative, so you get a big negative right here. That's going to be sigma p. And then sigma r is right here, and we subtract it. So sigma p minus sigma r, and it equals the delta H given, the negative 4,000. Well, if you isolate for negative 2x, you end up with a positive 605.4. Divide each by negative 2, and you get this is our final answer. And this is heat of formation for isopropyl alcohol, or propanol. Here's a problem, and it's just like the one we just did, just like number 5. We're going to need to go up and steal some numbers. So we will need to have the delta H of formation of carbon dioxide equaling to negative 393.5 kilojoules. We will need the delta H of formation for water. Ran across a problem while looking at this. This is the heat of formation for liquid water, and here's gaseous water. And the problem down here is gaseous water. So we really needed a different number that's a negative 241. But since I told you to use these numbers, we're going ahead and use the one up here, which is 282.8, negative 282.8. This is when a teacher messes up and says, I just want to see if you can catch it or not. So when you look up these numbers, you're going to have heat of formations of water on top of each other. One's going to be a gaseous one, and one is going to be a liquid one. And they're differ by the heat of vaporization. So they're going to be off by nearly 40. So given this, we don't have this guy right here. This is a balanced equation, and you'd put it all together to make it equal to the delta H given. So I'm going to see if you can do this one on your own. We're going to solve for the combustion of naphthalene, which is C10H8. And honestly, it's easier because you have X and not 2X. So I think the number 5 question, which is almost identical to it, is actually more difficult because you actually have 2X as opposed to X. I hope this helps. I can give more examples if you need to, but they're all done exactly the same way. You really have 2 kinds of problems, one like number 5 and one like number 6, and they don't really vary much. But first and foremost, learn the definition for heat of formation. Understand if they're talking about a heat of formation equation or using heat of formation to solve for a different equation. Thanks. I'll see you later.